the proof assistant rock, used to be cock, named for Kokand. Formal definition here. If you look at this, you see the standard constructors of untyped lambda calculus, which is the variable, application, and abstraction, plus this S thing, which is two sorts, star and box. Star indicates a type, box indicates a kind. And then this, what's called a pi type or dependent product that characterizes the type of functions. Now, because in lambda calculus, functions are the only values that are there by default, this suffices to ground out those values. So you can take, for instance, the identity function, and that says set A to star, then X is a type, and A here is X. So that says for all types, we return that type. So that would be an instance of, this is a generalization of the arrow type in the simply typed lambda calculus. So then there are a bunch of inference rules for beta equivalence. There are a bunch of inference rules for typing. The thing to note is that in here, both types and terms are part of the same grammatical production. So I can apply a type to a term, or, I could apply star to box, whatever that means. But then down here, we pick out the well-typed subset of terms. And so applying star to box doesn't work because in order to get an application here, you need to have something that's a pi type there. And neither star nor box have a pi type. In order to derive that something has a pi type, it's got to be a function. So, that's not something that is well typed.
Is box typable?
No. No, that's part of the hierarchy, is that it stops at box. Now, there's a concept called the pure type system where you can add more layers and more different levels of kind, but this is the prototypical one.
Looks like Charlie has his hand up.
Sorry, I can't see.
Yeah, it's okay.
Go
Charlie?
ahead.
Yeah, and this may be just me not having enough mathematical knowledge or enough familiarity with the lambda type system, but can you briefly, if possible, tell me what the difference is between a kind and a type?
Yes. So there's this colon here that is a relation on the terms of this grammar. Okay. This colon associates something of a lower level to something of an upper level. So a type would be, for instance, the type of the identity function. And the question I was just getting to is what uses of star and box are permissible? So here's the list of different calculi. This one is the simply typed lambda calculus. Here, only star is permissible. So the only thing we can do is put star in for S1 and S2. When we put in star for S1, X colon star means that X is a type.
So Charlie, to inform your intuitions a little bit, as you go up the hierarchy, you're losing specificity. So terms are very specific. Types erase some of the structure of terms, and kinds erase some of the structure of types.
Mm.
So you're losing specificity, and in the process of losing specificity, you can think of colon as an analog of membership. It's not exactly membership in this system, but it's close. So when you say a, like a term colon a type, you're saying that the term is somehow a member of all the terms that bear witness to the to the type. And likewise, when you say type colon kind, you're saying that roughly speaking, that the type is a member of all the types that are witnesses to that kind. Does that help?
It does.
In
So
in polymorphism, or sorry, in this, we've got type operators. This is, for instance, um, very close to Henle-Milner generics, right? In Java, you've got list of int, ditto in Go and Rust and all of your favorite programming languages that have parametric types. So the pi operator here is playing a double role. When S1 is star and S2 is star, then this says this is a type of a term that takes in a type A and returns a type B. So A arrow B is, even in meta, you've got A arrow B as expecting a term of one type and returning a term of another type. So this characterizes those functions that expect an A and return a B. If S1 is box, then then we need something where we can derive A colon box. And we've got one of those here. It turns out that you can construct others depending on the calculus, but at least we know this one here. So this says A is star and S1 is box. And so in that case, X colon star says X is a type. See, before it was A colon star. That means A was a type and X was a term of type A. Here we have star colon box, and X colon star means that X is a type. So now this thing is something that reads in a type and returns a type. Well, that's like list of int, right? You give it int as the input, and it returns list of int, the type, as the output. So this is playing the role, depending on what S1 you choose, of either a lambda term that is a program, or a lambda term that is a type function that turns one type into another one.
thank you.
Sure.
In your example, so S2 would also be
in that example, S2 is star. But if we make S2 box, then we get some other language features. So if S2 is box and S1 is star, then this says X is a value,
right,
whereas B is a kind. And so that would say, supposing that B were star, that would say that for each value we return type we return star itself. That doesn't depend on X, but we get a copy of it. And so the result is that it ends up being polymorphism in that case. And then we get dependent types where for each value we return a type. So if B colon star here and X is a value, then for each choice of X, we get a type B. So for example, in a struct, say A is the set of field names X is a choice of one of those, we get the type corresponding to that field name. So by varying these S1s and S2s, we get these language features here. Dependent types, polymorphism. Polymorphism here is like the identity type, where you say, given any type alpha, it has it's a function from alpha to alpha.
Mike, would you mind going back to the term production?
Term production, right here?
No. The production for all the terms.
The grammar, yeah.
Yeah. So I just want to point something out. This is clearly a fixed point expression. And it's a fixed point expression which includes typing, right? So now we're saying that types are terms. And when Mike is done with this presentation, I want to recall that fact and relate that to AI. Okay? So we'll go through Mike's presentation, and then I'm going to make some points about how this relates to AI specifically.
But to include typing, you have to modify the grammar, right? Because it doesn't include typing.
No, this does include typing. Right there.
By the pi?
Pi is type.
Right. But
okay. So pi is a type. S is the sorts, which are kind and type and kind. So this is like the capital T type, the type of types, as it were. Not quite that, but you can think of it sort of that way.
So Nil, the grammar that doesn't have the typing included would be if we drop the S, we drop the colon and the pi and the colon A on the abstraction. And that gives you the ordinary lambda calculus. And what Mike is going, just the high level, Mike is going to show you how when you have one of those grammars where you don't have any types at all, how to automatically get from there to a Baredregt-like system where the types are included as terms. That's the essence of the hypercube functor.
Yeah, it's to add S and pi and colon to an existing grammar.
Yep.
Okay. Okay, I get it. Thank you.
Yeah, so here we have a formation rule that is sort dependent. And here we have an introduction rule where we add this middle thing here. See, this B becomes that C there, the S2. These two are the same assumption. And this middle one here says now we're constructing a value B of type C based on these assumptions. Then we can curry that assumption and get the lambda. So we've got a bunch of axioms, these two things. Now, one of Greg's insights was to say we can characterize the pi type as a modality. It's called a rely possibility modality, where pi x colon a dot c means the set of terms that when you apply it to an A named X, the result in one step is possibly a C. Now in lambda calculus, here they mod out by beta reduction. So it's even when it's formed in 0 steps, it's a C, but because the subject reduction theorem, it's always a C, but it specifically in one step, it can become a C kind of trivially. But if you're looking at a calculus like pi calculus, then there's some choice as to, or at least non-determinism as to what the type becomes. Depending on which subterms synchronize, you will get different behavior, and you can't identify those without collapsing the entire type system to triviality. The contention is real, and then the resulting terms satisfy different propositions. So this part of a general, this part here is specific to lambda calculus itself, and doesn't really generalize. But the rest of this does to a large extent. So my idea was how much of Baredregt's construction can generalize to an arbitrary operational semantics. So we start with a lambda theory, which is the language in which we write down the operational semantics. We have these axioms. Gamma is a typing context for variables, so I'll call it a variable context. Delta is a typing context for relations, so I call it a relation context. And psi is going to be some judgment. And it's usually well, it's always a proposition, but there are three main forms of proposition. One is declaring that something is a relation, or declaring that something is a proposition. Relations are a special case of that. Asserting equality and asserting typing and kinding judgments. So because I'm mixing category theory, which has its own use of colon, with this typing kinding relation, I've added double colon here as the relation on terms that is being added to the grammar. We also make use of reductions of terms that P reduces to Q in a single step. And so this relation, the reduction relation, we denote with the squiggle arrow. So for example, we always have this axiom, which says that reduction is a proposition. Does P reduce to P prime? And then we can look at something like lambda calculus and say, if we have P, P prime, and Q that are processes, and we have that P reduces to P prime, then the application of P to Q reduces to the application of P prime to Q. So this says in what contexts reduction can occur. So if we have some reduction here, we can do that same reduction in the term context where P is in the head position. This is the definition of normal order reduction in lambda calculus.
And notice this is really important when it comes to meta, right? One of the critiques that we levied for meta was it didn't have a way to specify the only, a rewrite rule can only happen in these contexts, right? So it's you could simulate that by using resources, but this makes it explicit within the formalism.
So then,
I'm sorry. The axiom doesn't make sense to me. By virtue of being processes, it may be the case that one reduces to the other in one step y. I mean, that's a weird axiom.
No, this is just ordinary.
this is the normal order reduction axiom. It says
no, but it's written, for example, above that. For example, we always have the axiom.
Oh, this
that
thing?
if P, yeah.
No, this says that given that P and P prime are processes, we can ask whether P reduces to P prime. So this is what we can ask whether.
So prop means
prop
ask?
Means
I don't understand.
Yeah, prop means that this thing is a proposition. This
Oh, I see. It is the case that it is a proposition.
Yes.
Okay. All right. And you wouldn't use a type for that, or a kind, or something? It's interesting.
No,
Let's
types and
do.
kinds don't exist yet in lambda theory. So a lambda theory is just talking about the operational semantics. And then we will add to the lambda theory specific stuff for typing and kinding, which is Baredregt's approach to a type system, not a not a canonical approach to a type system. So there are lots of different ways one could do typing. Baredregt's lambda cube is one of them, and I'm attempting to generalize his approach to typing lambda calculus to typing arbitrary operational semantics. So the typing and kinding come in later, and I'll show you that. But this is just the basics of the theory that we use to describe operational semantics itself. So we always have the ability to ask whether one term reduces to another one. In the specific case of lambda calculus, we can make use of that to say, if it reduces, then in this empty context, then it also reduces in this term context.
Is this axiom an actual axiom, the
Yes.
one P implies P prime prop, or is it more like a meta axiom that you
Well,
don't really formalize?
This is an axiom.
Okay.
And Christian Wells has written up a big paper about this being part of a presentation of a lambda theory, which is a category with finite limits, closed with respect to the product, with a distinguished object called PR and a distinguished relation that is the squiggle arrow for reduction. And that structure is enough to specify the operational semantics of any virtual machine. This part of it is the distinguishing of this relation on processes. So
Okay.
this is one of the kinds of judgment we can make, is that some symbol is a proposition, is a relation.
Okay, thank you.
And that stuff there is talking about what I just mentioned. Here's an alternative description, is that we have this category sitting above the theory itself, where above each object in the theory, that is each syntactical construction like nouns and verbs in English, here we have processes and names in the pi calculus, for instance. These very fundamental, different shapes of grammatical construction that we care about in the calculus. So above each one of these, we have the hiding algebra of subobjects of that thing. So there's a canonical way of getting these subobjects, and that lets us write down these comprehensions, these propositions about the types. Go ahead, Greg.
Yeah, thank you. Can you go back to the lambda page for just 1 second? No,
Oh, this one, yeah.
The Baredregt, yeah. Okay, so if you look at this system, like go all the way up to the production, okay, just being able to write down this grammar implies a bunch of structure, right? So those vertical bars, they're really co-products, right? And then the application, that's really a product. And then if you go down to the rules.
Yeah, the abstraction lets you do closedness, the bindings.
Yeah, exactly. And then all of these rules, they imply a bunch of structure as well. So you kind of can't get like whenever you try to write down something that has, at least Turing completeness, you bring in all of this structure, which which category theory is trying to take very careful account of what's all the structure there. Of course, category theory itself also, needs a bunch of structure just to write it down. So I just want people to be aware that there's always this ambient structure that is supporting anything that we write down formally. Is that making sense? Like the Baredregt stuff looks so elementary and simple, but when you try to take careful account of everything that's going on, all this structure is actually present. And so when you formalize it in category theory is saying, well, actually, we've got to have a list of all these. We've got to have a bill of materials, a bill of goods, a manifest that says all the things that you needed in order to express those rules.
Mhm.
And so part of what Mike's presentation is doing is taking careful account of that. And once you have a careful account of that, then you can build stuff above that. And that's what the logic does. The logic says, well, now that we know we're living in a certain kind of category with all these bells and whistles, then we know how to build other kinds of categories on top of that. So hopefully that makes sense. So like Mike is just saying, like just even to write down the theory of a monoid, for example, you have to have a
Yeah.
bunch of structure.
Mhm.
So there's this mathematical field called universal algebra. And the idea there is that we start with a set and equip it with some functions satisfying some relations in order to describe a mathematical structure. Bill Levere, back in the early 60s, said we can capture all of universal algebra using category theory. And the language we use to describe our mathematical structure corresponds to functors and natural transformations and equations on natural transformations on the categories. So here, to write down the notion of a monoid, we need to be able to mention an object, and all categories have objects, so that's fine. But to talk about multiplication, we need to be able to pair up the inputs in some sense. So we've got to have a tensor product with a unit. Now, the normal notion of tensor product is the product, the Cartesian product. And that says that we actually get literal pairs here. But in general, we only need to be able to put them together. We don't need to be able to take them apart again. So we denote this with the tensor product. Here's the unit for that. And then we have the associativity rule, the left identity, and the right identity, left and right units. So being able to say there is this object equipped with these morphisms that generate all of the other possible morphisms. So this implies that there's a morphism m tensor E that goes from m cubed to m squared, where we multiply the first two elements. I'm sorry, m tensor E that goes from m squared to m squared. We multiply the two elements and get the result and the identity as the second element of the output. So we can combine these in parallel, compose them, etc., to generate all of the morphisms. And then we insist that they satisfy these relations. So then a model of this theory gives us all monoids when we take models in set. So M is just a formal object, but when we take a model of it, we have to choose a set for M. And this has to be, we have to choose a function that goes from M cross M to M. We have to choose an element that goes from the terminal set to M. So we pick out one element of M to play the role of the identity. And those functions have to satisfy these equations. So every monoid arises as a functor from this theory to the category of sets. Now, this is useful because we can swap out sets for something else. If we take the category of vector spaces, then M picks out a vector space. Little m picks out a way of combining vector spaces in a linear way. E picks out one particular vector such that this stuff holds. This is an associative algebra. If we take the category of endofunctors, well, M has to be an endofunctor on some category C. M tensor M is the iteration of two endofunctors. So doing it twice to doing it once. So for example, we've got the list endofunctor that takes a set and returns the set of lists over that alphabet. This says, given a list of lists, return a list. And this says, given an element, we don't apply the list functor at all. Give me a list. So this is flatten, and this is wrap the value in parens. Associativity becomes a statement about the order of flattening. If I have a list of lists, it doesn't matter whether I flatten the inner or the outer first. This one says, if I have a list and I put parentheses around the entire list and then flatten it, I get back to where I started. This says, if I have a list and put parentheses around each individual element and then flatten it, I get back to where I started. So this characterizes a monad. This same theory, depending on where we interpret it, gives us a vast number of really important constructions. And once we understand one of them, once we understand the theory, then we understand what it means for any other context. So the idea of a theory having an internal language where I can say tensor and I can say unit is important. And so what we're doing in meta-IL is saying you can write down a theory and you've got a whole bunch of things that you can use when you do that. It is closed, so you can talk about binders. Right here, lambda x is a binder. In pi calculus, for x from y is a binder. It binds x in the body of the for comprehension, or the for process, and so on. We have products, so we can talk about two terms. We have finite limits, so we can talk about propositions. So the structure that is put on the category determines the internal language with which we can write down an expression like this. So that's the idea of a lambda theory, is we've got a nice grammar that's like BNFC, but also has binders and also has propositions.
So just to amplify the point that we've been making here, by being so anal retentive, by being so obsessive compulsive about the bill of materials that goes into writing down the theories, the payoff that category theory gives us in this regard is this vast amount of abstraction. Right, and then Mike just gave you a few examples of the kinds of abstraction that get accounted for when we're very, very careful about all the things that we need in order to write down theories. Does that make sense to folks?
Yes.
Yeah, and so in order to describe this language, which is essentially category theory, well, you have to use another ground formalism, which is category theory or is not category theory, or
Well,
is
the language
I don't know
is
exactly.
So the language is not category theory per se. So what we're saying is that meta-IL is actually a kind of it's a special language, and the reason it's special is because it has this microcosmic relationship to the category of all lambda theories. So just to like if you want to write down a lambda theory, when you have to have this bill of materials for a given category, and then meta-IL sort of becomes the internal language for that category, right? So
So
meta IL
DNFC,
somehow,
for example, can
yeah,
describe itself, right? It has a
exactly.
grammar, but it describes its own grammar using a grammar.
Yeah, exactly.
Um,
And it's the same.
Similarly, meta IL can do that, but also does it with binders and propositions.
Exactly so. Exactly so. And so what you get is this picture of the category of graph structured lambda theories as a graph structured lambda theory. Now, there are all kinds of caveats about, finitely presentable and all of that, right? So there's all these wild and woolly pathological behaviors in the category of graph structured lambda theory that, trying to write down in a finite way will be hard or impossible. But for the ones that where we know how to reduce them to actual running on devices, Meta IL captures that. And so it's special in a certain way. Like it is it's identified by the category of graph structured lambda theories.
So this is just how we write down operational semantics, is using one of these theories. And then the hypercube functor takes an untyped theory and adds types to it. And I'm going to get into how that happens. So we start with adding for each object of the theory. In lambda calculus, they only have one object, its term. But in pi calculus, we have terms and names, for instance. So for each object in the theory, we add a notion of type and kind. Now, this colon here is saying that this thing is a term of that type, of that, let me say shape. So this is a term of this shape. So if X is process, star is a new process, and box is a new process. We can think of these as morphisms from the terminal object to this one. Then we also introduce a typing kinding relation between elements of this object, elements of this shape. And then we say that star is related to box. So this
So
gets,
that's really an axiom scheme, right? That's for all the X's.
yes. We'll often leave off the superscript on the double colon because you just look at either side and see what it's talking about. This is the generalization of the dependent product and abstraction rules here. So these two rules here are these two rules here. And what this says is, go ahead. No? Okay. So we're going to fix a base rewrite. So for example, beta or the COM rule that don't depend on some other rewrite as an input. Then we choose a subterm of the left-hand side, L. And we say that has shape Y. And then the context is whatever is left over to surround it, so that we split the left-hand side into two parts. There's the context that contains the subterm J, TJ. And put together, we get the left-hand side. So for instance, let me scroll down a bit here. Right. So this is the beta rule. It says, given a function from processes to processes and another process to apply it to, we can form a process with the lam constructor that turns that function into a process itself. And then a app form a new process that is the application of this lambda term to that value. Now, the way we've done this here with the arrow internally means I don't care how you handle variables internally. You may use de Bruijn indices, you may use named variables, you may use combinators. I don't care how it happens. This just says there is a bound variable here and it produces a body. So this lam turns that particular function into a term of the language. And then it says, if you have this construction, then it rewrites to the application of that function to that value. So this is saying, however you've implemented binding, now do the corresponding substitution. So this is what it means to have beta reduction. We're using the built-in reduces and saying, okay, here's what we mean by reduction. So then we start with a subterm of the left-hand side of this rule. We're going to take lam f as the particular subterm we care about. So that's T1. Y1, the shape of that subterm is a process, right? Lam f is a term that we can think about. The context is application with a hole in the first slot and x in the second. The free variables of the context is just the set containing x. And what we get is a modality here. This says those terms that when you put them into the context C1 and assume that x here, this free variable, is related by the typing-kinding relation to the type A, or kind, possibly reduces in one step to B. So those terms that when you apply it to an x of type A, you get a B in one step. This is exactly the dependent product characterized by behavior. And so when we scroll back up here to the formation rules, this says if AK are a bunch of types and XK is the right shape and each variable XK has that corresponding type, if in this context here we can deduce that B is of that sort, then the modality that is this dependent thing on the X's and produces B has the same sort. So that is exactly what occurs here. Given A has this sort and X has that type, implies that B has this sort, then we get this modal, we get this type operator that has that sort. Similarly, for the introduction, we add this bit, which says, if in a context where all of this stuff holds true, and we know that T in that context reduces to P, if that entails that P is of type B, then we say that T itself is of this modal type, a thing that when you put it in that context reduces to a P of type B, right? So this is the introduction rule for how do we get a term of this type, whereas the formation rule says how do we construct the type itself. So these two are very direct generalizations of what Baredregt did here. And it specializes in the case of lambda calculus to exactly what Baredregt did. But now we can generalize it to an arbitrary reduction rule. Anytime we've got a base rewrite like beta or com or what you're doing in a Turing machine state that says, well, read the cell here, and if you're in this state and change it to a 0 and move one step to the right, all of those different models of computation we can express as rewrite rules and then derive these modal operators from them, one for each subterm. Now you might say, okay, but application has two subterms. What happens with that one? Well, it turns out there's a notion of closure where you say, what are you fix some B that is a desirable property like termination or satisfies some security proposition. And then you ask, what are the values for some set of functions that, or some set of contexts that allow the context to evolve and preserve that good property, or to evolve into that good property. So you talk about good values, and then you can do a dual that says, what are all of the functions that preserve the good property given just the good values? And so there's this double negation that goes on, where you can get a closure operator that says these are the values that are good for all good functions on these values, right? You expand either the set of functions or the set of values to the largest possible collection of functions that are all good on these good values.
If I might interject two comments right here. So one, what Mike just described, for those in the know, that is closely related to Girard's phase semantics for linear logic. That double negation thing, there's a general construction going on here that is closely related to the phase semantics for linear logic. But the broader point that I want to make, which is connected to AI, what are these contexts? These contexts are programs with holes in them. And that is what we'll find running all throughout this work is different ways of knocking holes into programs, and those as schema. Programs with holes represent ways of compressing an understanding of a collection of programs. That is from the point of view of any computational entity that lives inside a lambda theory, its fundamental way of viewing the universe of phenomena around it, and the only phenomena it can ever experience are other computations in its own model of computation. So its way of understanding, characterizing, classifying its environment is in terms of programs with holes knocked in them. So this is part of the story. It's like if a computation wants to understand the behavior of things in its environment, it uses the modalities. And then and what you'll see later is if a computation wants to understand the structure of things in its environment, then it uses the structural types. So sorry, Mike, please go on.
Yeah, no worries. A program with a hole in it is also a query, right? Any type is a query from the set of all programs. It says, give me the subset of these programs that satisfy this typing relation. So give me all the things T that satisfy this, right? So we can provide types as queries to a source of programs and extract those programs that match that type. Now, usually types are talking about the shape of data being passed around, but this talks about the behavior of the program terms being passed around. So we can ask for things that do a certain thing rather than things that accept data of a certain shape. So that's the reason that we like to look at modal types, is to characterize the behavior of stuff.
But it's not just programs with holes in them, right? It's program, yeah, potentially with holes in them.
Well, this
going
modal
through some
is,
computation. What?
Well, the whole idea of this modal type is CJ is a program with one hole, and these are the types of all the other variables left over. Right? So this CJ literally is a program with a hole in it.
Well, okay, all right. So when you say a program with holes in it, you mean it not only it has holes, but it actually computes over the holes to produce new holes in a way.
Yes, yeah, we're taking a specific program, the left-hand side of the rewrite rule, so that when you fill in the hole with the given subterm, we know there's a reduction, right? We're choosing this special class of programs with holes in them, but
It's
still
literally
just, yeah.
what he's saying right there is CJ of TJ equals L. That's the splitting of the term of the left-hand side. So we know the left-hand side rewrites to the right-hand side, and we're going to take the left-hand side and split it up into C, which is a program with a hole in it, and T, which are things that if you fill the hole, right, it will form a proper left-hand side and rewrite. So C is
Yeah.
literally a program with a hole in it.
And you can see that
Right.
in that example we looked at earlier, where what dependent product special case, right? So there, that is the program. This is the hole. And if you fill this with a lambda term, then there will be a reduction. So the modality says those things that cause a reduction when placed in that hole. And so then the introduction rule says, well, lambda terms are the things that will cause reductions.
And this is and now if you go back to the origins of computing, right? Lambda calculus is the first calculus that we see where you're beginning to get the idea of the power of programs with holes in them, right? Abstraction is another way of writing down a program with a hole in it, right?
Now, we're down to the last minute, so I just wanted to make the one last point that we've got these S's here, these sorts. So we've got a choice of S's for each of these AK and a choice of S for the final B. These, in the special case of the first slot of application in the beta rule, give you the dependent product here, but we get this whole hypercube of calculi depending on whether box is allowed in that position or not, right? Similarly here, we have a whole bunch of variables that could have a box in that position or not. So in the COM rule, we have an extra variable, right? The channel on which the message is sent, not just the value that's being sent and the binder on the other side, but the channel over which they're being sent. So we can choose a sort for that one. And that lets us think about calculi in which we can send names over types as well as sending names over, sending processes over name types as well as sending processes over names.
Right.
So that introduces this expanded universe of kinds of calculi we can reason about. And they're all related in a hypercube based on whether these SK can be boxes or not. Now, there's some subtlety to this, but we're out of time.
Well, I mean, quite often these run quite a bit longer.
Okay, in that case, let me
some others
one
have
example of
meetings
a
too.
subtlety.
Yeah.
If we'll get down to the structural types later, but suppose we just look at par, which takes two processes as inputs. Naively, you might think that you could apply that you have two choices of whether to have box in a position or not. But because par is commutative, it's really only one. And so later in the paper, it talks about finding the equational center of the operational semantics so that you limit the dimension and figure out which sorts imply other sorts so that you have the right number of choices here that give you the size of your hypercube. So go ahead.
So I was just going to say, for those who want to stay, I've got at least another 15 minutes before I have to go do something else. For those who do have the time, there's more to talk about here.
I've got another half hour, so
feel free.
So-
Those who need to go, please go ahead. But let's take
Can
some
you-
questions.
Can you post this someplace? It's not going to be as clear as when Mike goes through it to read it up by myself, but
Yeah, I can share the link. There's a whole lot of presentation that needs to change. There is still a little bit about negation later, but it's up to section 3 that is really what Baredregt was talking about. Now, it's possible to go beyond what Baredregt did and introduce other kinds of types. So this stuff talks about those slots and assigning box or not in that position. Um, to go be so I mentioned at the beginning that the Baredrect only needed to add the dependent type here to characterize these because these are values. You can get like the identity function doesn't reduce any further, and you can't. There's the subject reduction theorem stuff here that says every term that's typable is going to end up being a pi type. But that's not generally true. For example, the zero process is not something that triggers any reductions in any context. So we don't automatically have a type for the zero process in pi calculus or row calculus. So it is useful to introduce the notion of a spatial or structural type that talks about the shape of a term rather than what it does. So here we say for each term constructor, we introduce a new type constructor that characterizes those terms built this way, whose topmost node in the abstract syntax tree is F. And then we can choose slots or choose the sorts for each input and for the output. That will give us a hypercube. Now we have to mod out or not mod out, but we have to find the equational center to actually know what the restrictions on those slots are. But that's the basic idea. Is we introduce something that says this is what the shape of the term is. So then typing rules, formation is straightforward. We get to choose types for each of those holes, and then we say this is something that uses F as the topmost node, and its children have these shapes or behaviors. For introduction, anything built with F is of type F. For elimination, we say, well, if there's any proposition that depends on the top node being F, then that same proposition holds given that Y has the type F sharp, which is an assertion that the top node is F, right? So of course it'll work there. The semantics is very straightforward. It's just that subset of terms in the model that are built this way. Sorting this goes through that equational center idea. Here's the idea that alpha beta is commutative. I mean, par is commutative, so alpha beta is the same as beta alpha. So you don't actually have two different choices for these slots. When you've got, for example, a ring or a rig with addition and multiplication, then when you just going by the distributive law, Q and R have to have one sort. Multiplication can have a different sort in the first position by just this left distribution law. So these two aren't forced to be equal yet by this law. If we also introduce the right multiplication distributivity, then it would force all of them to be the same. So the equational admissibility demands this, and we can go on, but that's not a critical idea. For carrying on. So once we've got these structural types and the idea that these characterize sets of terms, then we can say, well, we've got logical operations on sets. Let's put those into the type system as well, because they're useful. So the structural types and the logical operations are going beyond what Baredregt did, but they still are a fairly natural thing to add to a type system. So here we add union, intersection, implication, negation, top and bottom being the full thing and the empty thing. Formation rules that say, well, they've got to be elements of the right object, and these types have to be of the same sort, and then we get this union that is of the same sort, and so on. So here's the formation rule. This one I got wrong. These should be separate. Two inference rules instead of one. This would actually be for intersection, but says if we have an X that is of the right shape and X has type A, and we can derive something about X, then we can derive the same thing from A or B. Intersection this is the elimination rule. It says given an intersection A and B, we can derive A, and similarly from that we can derive B. Implication, this is currying of the relation context. So given an assumption that X has type A, we can derive that X has type B. We can move that assumption into the right-hand side, and so this says X is something that, assuming it has type A, also implies it has type B. So then we have the elimination rule that is standard, that given an A, we can get a B from it. Top is trivial. Anything that inhabits the shape X. If T is a term and A is a type, and they're both of the right shape, then T is of type top X. And there's no introduction rule for bottom. Complement is sort of weird. That's still a to-do. But given bottom, we can look at the notion of negation relative to the modality. So this says those terms that when placed in the context J with variables of these types reduces to something in the empty set. Right? So what you'll get is if this if there are any terms that cause a reduction, this is necessarily empty. But if there aren't any terms that cause a reduction, then it's all of all processes. So this is an inhabitation negation. But there are different kinds of negation based on each of the different contexts. So this is negation relative to a certain subterm of the left-hand side, as opposed to the Boolean negation, which says given a this is the interpretation down here. So if we've got a shape X and a term little x and a type A, we can negate A and say it's those terms that are of the same sort. This is wrong. I fixed this before, but there was a reversion. We get rid of that bit, but this bit is right. It says those terms that are of a type B that is the same sort Sx that excludes A. So if we did this naively, just negation with respect to all terms of that shape, we could negate a term and get a type and star and box as elements of the negation, right? Um, we want to negate things relative to the subset of terms that are at the same typing kinding level as the one that we put in there. So
Yeah.
by restricting negation to A and saying A is at this sort SX, we then get the complement that is also of that sort SX. And that keeps the makes it sensible. So the negation that's due to modality is different than the Boolean negation here in the models. In order to introduce Boolean negation, we would have to introduce coproducts that says if we split the set of all terms into two parts, A and B, that are disjoint, then if we know that X is of type A, we know that it's not B. So because I haven't added disjoint union yet at this point, there's no introduction rule for complement.
Right. And in fact, you don't have to go back and retrofit what's done up to this point, right? We can say, in order to do this, we now have to add co-products to the bill
Yeah.
of materials, right? And that kind of that seems to be the dividing line between type systems and logics is, this ability to do this splitting over the universe, right? So up until this point, the type system is not strong enough to do this kind of complementary negation. But when you add this kind of complementary negation, then you're explicitly saying, something about the universe of models that this can live in. So that's very key. Uh, uh, it's like a dividing line where you've got a type system and where you've got a logic. Now there's to relate this to AI even further, right? So
Before you get into that, it's
okay,
9:45. You said you had 15 minutes.
yeah, I have just enough time. I've got something I've got to prepare for, so I can. It's a little squishy, but thank you. Okay, so the point I want to make about AI is that again, what we're trying to build programs that can understand their environment. The only environment they can ever understand is collections of programs in the model of computation they were expressed in. That's it. They are ontologically isolated. That's really important to understand.
Similar to how our brains can only understand the sense signals that are being injected as electrical signals into the brain from whatever organs we've got, right? It's not that we are directly perceiving light, it's that the light hits the retina, which causes an electrical signal to go into the brain. And it's just that electrical signal. In the same way, a computer can only understand a program because that's
Yeah,
the only way it has to interact with its sense information.
exactly so. Exactly so. That's why classification for a computational entity in a given model of computation, classification natively is programs with holes in them. And once you understand that fact, then the next step in the puzzle becomes important. If a program wants to be able to reason about its own reasoning methodology, like if a program, so science, for example, implies a certain kind of reflection. Now, what do I mean by that? So when a scientist is formulating hypotheses, the ability to formulate the hypothesis has to be something that the scientist can do. And we've just said that the hypotheses, in other words, a characterization of some property of its environment That's a hypothesis. That's going to be a program with a hole in it. So for the program to be able to work on hypotheses, those things have to be programs because that's the only thing the program can ever interact with is other programs. So the programs with holes in them, which are the basis of types, they have to be programs. So that's why Mike's hypercube functor is so important from an AI perspective, right? Because it tells you how to do that fixed point operation. Given a notion of computation, how do we build a scientist? Well, a scientist is something that works on hypotheses, and those hypotheses are effectively programs with holes in them. And so those things have to be programs. We have to reflect hypotheses back down into programs. And once you have that capability, then you can complete the scientific method, the loop. So the loop is you write down a hypothesis, a program with a hole in it, and then you test it. Well, how do we test it? Well, we go and we take some stuff from our environment and a model, a program that represents something in our environment or a hypothesis about that, and we put that in the hole. And then we can complete the computation, and then we check that against what happens in the environment. What do we actually see? Right? And that gives us the ability to compare hypothesis against experience. And once we have the results of that, then we can go back and revise our hypothesis. But again, revision of a hypothesis is computation on programs with holes in them. So effectively, the hypercube functor is the minimal amount of apparatus that you need in order to build a scientist in the technical sense that I'm talking about a scientist. Does that argument make sense? It's a step-by-step, careful argument about what has to be in place, starting from a notion of computation.
Yeah, to me, it makes tons of sense. And now I understand what you mean, programs with holes in them that compute. Because when you say that, I thought, well, yeah, but that's not powerful enough, just to put holes in an expression. But then if you add the computational aspect,
Yeah,
then it means you can basically you can categorize arbitrarily finely what you want to how to say the set of of programs essentially
yes.
that you're talking about. And the other thing I wanted to ask is terminology question. The reason you call that hypercube is because you have multiple objects,
Yeah.
not just you don't
But
have
we have
just
multiple
star and
axes
cube.
right here. See how we've got these three axes for dependent types, polymorphism, type operators. These three axes come from
They
um,
come right. They
these
come
two
from
things here because we have two different choices of S1 and S2
right.
and two different
Yeah.
choices star or box, and one of them is
Mhm.
already accounted for, so that's 2 squared minus 1 is 3 axes. When we get to the
Mhm.
com rule, there are 2 to the third minus 1 is 7 axes, so we get a 7-dimensional hypercube rather than a 3-dimensional cube of calculi.
Because there are names and processes, right? In
Yeah.
Lambda,
Well,
there's
no, it's not
only
that there are names and processes. It's that there is the um, the input and output of the body of the four, the receive, but there is also the name on which it is sent.
that's
So,
what I was saying. Names and
oh, okay.
processes. Yeah, yeah, yeah.
I thought you were talking about the fact that there were name shapes and process shapes.
No, no, no. Yeah.
It
Anyway,
was a
yeah.
specific form of the com rule. Yeah,
Right, correct. Right, exactly. They're names and processes in the com rules. So
yeah.
yeah, so you get that many dimensions. And depending upon the model of computation that you have, you will have a varying number of dimensions.
Yeah. How many of these S1 assertions? So here in the formation rule, back in 3. right there. We have k different ones here. So it'll be, assuming they're all independent, 2 to the k minus 1 axes.
So yeah. So kind of the point that I'm trying to make here is that this is a step by step a way of constructing, like, from each value prop or each assertion that AI makes to the community, right? So AI says that intelligence, at least important and interesting and useful aspects of intelligence, can be faithfully rendered as computation. As soon as you make that step, right, then all of these implications, come into play. Like, that may or may not be the case. We don't know. But if we take that idea that some aspects of intelligence are computations, then all of this stuff follows as a result of that assertion, right? So you have to be able to say what a computation is. That's the category of lambda theories. That's the very first step, is what is a computation? Once you know what a computation is, right, then how would a computation, so we're now saying that computations are intelligent critters. Okay, so what kind of activity identifies the intelligent critters? Well, doing science is one of those. And we know what the scientific method is. And the scientific method requires that we can compute over hypotheses. So you have to say what a hypothesis is, and the Hypercube Functor tells you what a hypothesis is, and gives you the ability to produce the fixed point. And then I'll leave you with one final notion. Every model of computation is really telling you a theory of causation. And this is what differentiates this whole approach from the large language models. The large language models have a single built-in theory of causation. Predict the next token. That's it. That's the only notion of causality that's there. What we're saying is each model of computation is a hypothesis about how causation works, right? The left-hand side is the state where we are. The right-hand side is the state we evolve to. That is causation. And everything that we're doing here is how to make hypotheses about some environment that we live in based upon that theory of causation. And then the steps that go beyond that have to do with mapping from one theory of causation to another theory of causation. So when we map the lambda calculus into the pi calculus, we're saying how the theory of causation in lambda that's implied by lambda is related to the theory of causation that's implied by pi. And so hopefully, to make it pithy, right? Every model of computation is a karmic theory. It says how karma operates. So with that,
I would like to just make one more point.
yeah.
The stuff up to section 3 is what Baredregt did. It is a very limited notion of typing. The structure we get from a lambda theory includes the ability to talk about propositions. Now, if we keep it as part of the lambda theory, then we're able to describe the operational semantics in terms of these propositions. But what we would like is to turn the ability to make propositions and ask questions about the terms. We want to give that ability to the programs themselves, not just the description of the program. So the rest of the paper about the structural types and the logical operators and that, That's just sort of inching towards what we've already got in the lambda theory. And so Christian's approach um, is going to be one, this is a nice demonstration of a useful thing, but all of this is encompassed by the language that we already have. So he's working on taking an untyped lambda theory and adjoining the structure of a finite limits category. So we get the internal language of that rather than this very simplified version that I've outlined here.
Yes, so I need to give a caveat, right? The thing about the finite limits theory is that it forgets the context stuff, right? So what I'm trying to drive here is with the programs with holes, that gives us enough to recover
Right, but we
programs.
can characterize this particular modality in exactly this way. This is an expression in the finite limits theory.
There we go.
And
Yes, yes,
so
yes.
so we can capture all of the meaning of the modality in the finite limits theory. We're just
Yeah,
picking out
yeah.
specific relations that we care about in this approach.
Right, right. Yeah. So, but what I'm trying to argue though is that if you started from the finite limits theory and didn't think about the context, then it
Yeah,
becomes
this one shows why it's important to consider these ones, this particular.
exact
Yeah.
exactly. Yeah, that's the critical thing. And it comes down to something very practical, right? People have been trying to do program extraction from proofs in a practical way for a long time. And if you're way out there in predicate land, then you don't have enough information about the structure of the programs. What thank you, Adam. Ciao, ciao. For the if you want to do real program extraction from proofs, then the context become the thing you have to focus on. So that with that, I also have to jump off.
Me too.
Thank you all for the ability to present these results, and thank you, Mike, for driving them forward. This is some of your best work. I love it. And yeah, hope everyone has a great rest of your day.
Thank
You
you.
too.
Very
Thanks so
trippy.
much.
Thank you.
Cool, cool, cool.